Hello everyone and welcome to yet another problem from Geeks for Geeks. Today we'll be seeing one of the problem which is named as square root of a number. The problem is quite simple over here. We are provided with a number n and we wanted to find the square root of it. But the catch over here is if it is not a perfect square, then we need to return a floor value. Else, if it is a perfect square, then we have your answer ready. We need to return the square root. The problem seems very simple and it can be done with a square root function. But do we want it to do that? Using the library methods is not a bad idea at first, but we are here to build logic. So instead of using the inbuilt library method, we are going to go ahead and write our own method which will compute the floor square root. So without any further ado, let's get started. So first thing what we required is we wanted to know what is the scope of this. So we have a number n. So we know n which spans itself from 0 to a number n, where this capital N belongs to natural number, is a natural number. I can say that, obviously. So now if that is the case, where would square root of n lie? So square root of n would lie on a very broad scale from 0 to n. Technically it should be square root of n, but we don't have that. That's a question we need to find. But we can have a rough estimate that, hey, square root of n should lie somewhere between 0 to n. Or for that matter, let's eliminate 0 for a while. If we know that, hey, if n is 0, then we know that square root of n is also 0. So result is equal to 0. But if n is not equal to 0, then that means the result is not equal to 0, or it may equal to 0 depending on the fact that if n is equal to floating point number, let's suppose 0.5. But in this case, we are not considering any floating point number because n is a natural number. So that case is eliminated. We are left with only two things, if n is 0 and not 0. So now considering if n is 0, then we can go ahead and just return if n equals to 0, return 0. But if that is not a case, we are left with two things, that left and right. So left can be 1 and right can be the number itself. I'll take it as long for better precision. Now we have initial setup clear. Then what we'll do over here is we'll just check whether within this range do we find our number or not. So now you see where we are going forward. So if L is less than R, then we are going to check. This is very similar to a binary search. So this is very similar to a binary search where we have a certain set of numbers or certain range of numbers from 0 to n, and we check from this point to this point do we find a number, or this point to this point do we find the number. So if we say that, hey, this doesn't contain our number, so we check from this to this, and we again check from the middle to this point, and we go so on till the point we reach a point where we get a floor of a square root. So that's the thing, and that's what we are going to implement within this solution as well. So we have our left and right aligned with ourselves. So let's go ahead for the check. So we'll have a mid. So I'll get long mid is equal to L plus R minus L divided by 2. So we got a mid element. We check if mid into mid is equal to n, because it might be a possibility that the mid we found itself is a square root of the required number n. So if it is that a case, then we return mid because we hit the jackpot and we don't need to go ahead and check further. But if in a case that we have a mid into mid which is still greater than n, then we are sure that our result lies in the left. Result is in the left. So in this case, we go ahead and assign right to mid. Why so? Because we need to trim the right section, and the better way to trim is assign right to mid. A general rule from binary search. And if that's not a case, in else part, we assign left to mid. In any of those cases, if we fall out of the loop, we are good to return left, because we want a floor element and left gives us the minimum. And there might be a case where we stuck in a loop in such a way that we have L and R simultaneous and we get mid is equal to L. What I mean is, if we have 2 and 3 and our mid would be 5 by 2, which is 2, and in this case we'll go ahead and iterate and iterate and iterate. So I'll just add a method if or mid is equal to left. In either of the cases we return mid. So let's compile it to check for the sample test cases. So sample test cases looks good. Let's submit it to check for against rest of the test cases. And yeah, the code looks fine. It has passed all the test cases. Do mind the time complexity of this algorithm goes in log n time complexity, and space is a constant because we didn't use any of the spaces. So this was asked in these many companies, and yeah, if you wanted to know more about this binary search topic, I have made a detailed video. Click the video on your right, and I'll see you in the next one.